In this case, there will only ever be one model. You're going to initialize it, you're going to train, and just keep on training it. And we're going to be testing, mid-train. So you'll train a little bit, then we're going to just pause for a minute and test it. Note that testing doesn't destroy the model in any way, it just uses the model. And so when you're done testing, you can just keep on training as though you've not done any testing at all. And that just works just fine. The model doesn't know you took a pause and used it for a while, so training just continues.
But once you train on the entire training set, you should have under.
That's correct, yes. And by trained on the entire training set, I mean, I think it takes about 5 or 6 epochs of training. Anybody have to take a whole lot longer than that? I haven't looked at your submissions yet. I see a lot of them were turned in.
So how many epochs do you think we should do before we get them? Are you saying that we should finish one entire?
I'm saying you should print results after each epoch and be sure to flush standard out. I hate that mistake. Every time I forget to flush standard out, I run my program, I wait for 10 minutes and I see nothing, and then I remember, oh yeah, I forgot to flush. And that means you don't know how long it's going to be till it prints everything to the screen. Is there a solution to that? I don't think there is. It's kill it and add a flush statement. So after every epoch, print your results and then flush the standard out, and then you'll see output as it's running, and then you can just watch it, and when you're done, you press Control-C, and then you're good. So I'd set it to run for, say, 10,000 epochs. That way, if you get to 9,998 and you just want to keep on going, you can. I don't know why you'd want to go that long. You should get tired of it after about 10 epochs, but you can that way.
And were we supposed to do some sort of random like randomizing the data set? Like you said, the index of the
yes. So
after we do one epoch, we mess up the training and the test data and do another epoch, right?
Yep. Oh, that's because I'm on the wrong ear. So basically, yes, I recommend that every epoch you reshuffle your data. Okay, time to introduce you to the next assignment, just to make sure you have plenty of time to get ahead on this. On that note, I was looking at the schedule and it looks to me like, yikes, that's a little tight. It's not really a huge assignment. And I do want to emphasize that this one, assignment 4, this isn't huge either, but I believe assignment 4 will cause more issues. It's more likely to have random surges of, you might have to take some time and debug this. Whereas I think assignment 3 is pretty straightforward, so it shouldn't take you too long, I believe. Now, my ability to estimate the length of time assignments take has proven very poor in the past. Whenever I say it's easy, students come back and tell me I was wrong. Whenever I say it's hard, students usually thank me later and tell me it was easy. So these are all killer assignments. Get started on them right now or you'll die.
Can you elaborate on point 3?
On point 3?
Yes.
Yes. But first let me finish the point I was making, which was, okay, I have 1 week to finish assignment 3 and 2 weeks to finish assignment 4, and then we go to spring break. Okay, after that, I have 5 and 6 down here. Notice things are a lot more sparse later on. That's because I'm going to inject some reading assignments. I promised to do that, I just haven't gotten around to doing that yet. But I thought it would be really great to do a lot of reading at the end when all your other classes are piling on work and have your programming assignments out of the way up front here. Do you agree with that? Mostly? Okay. Well, should I utilize some of this space at the end by pushing the assignments back to give you a little more time now? Nobody ever says no to time now, although that's not very forward-thinking of you. You'll regret it in the future, I promise. I'm not offering to reduce the load, I'm just suggesting that we can redistribute a little bit here. I'm thinking I will take assignment 3 and move it to be due Friday, just so that you feel you're not going to be having to get it done immediately. That doesn't give you an extra weekend, it just gives you a few more days. Does that sound pretty reasonable? And I'll do that with the caution of that now puts you about equidistant between 2 and 3 and 3 and 4, and I think 4 might require a little more attention, so be warned and maybe get ahead on your assignments. That sound fair? Okay. That will be the plan then. After class, I'll go move this to then, and if I forget, it's now recorded, so you can hold that against me. Okay. And how much time do I have? Great. Assignment 3. I want to briefly talk through this one. Okay. Make your neural net train support multiple layers. We've already done that. What? This looks like bad instructions. I think this was left over from somewhere. I apologize. I'll go touch up my instructions. Okay, add support for batch and mini batch gradient descent training. We've been talking about that already. Do you feel like you understand what that is? Do you need any clarification on it? Think we're good? Yeah.
We had to divide by the number, by the size of the batch. Because otherwise it gets huge.
So you will have to make the learning rate smaller in order for batch gradient descent to be effective. If you use the same learning rate, then it's probably too big. But dividing by the full batch size is often too much. So exactly what learning rate to use for batch gradient descent is not very clear. I don't know if there's a great way to determine it. So basically, your job is to do a little fiddling as far as the learning rate goes. One thing I've found is that with stochastic gradient descent, values a little smaller than 0.1 almost always do well. With batch gradient descent, I've never found a trend with the learning rate. If you take 0.1 and divide it by the batch size, that's almost always too small, so go maybe halfway between there and 0.1, and then it's probably good, or something like that. Maybe you can invent a better heuristic than that. I'm certain the literature is rife with all kinds of heuristics about how to pick your learning rate for batch gradient descent. I just haven't paid attention or read that part of the literature, so I don't know what the best value there is. Okay. Add support for momentum to your neural network. Let's talk about momentum. Okay, so as was previously mentioned, let's suppose this is where your weights currently are, and this is where your weights want to be, meaning this little x is the global optimum in the model space. So my axes here represent 2 of the weights, and pretend there are lots more axes, 1 for all of your weights. And so you're trying to get your weights from your random initial starting condition, which are probably initialized with small random values, mostly drawn from a normal distribution, because I said so, to down here. And batch gradient descent is going to follow whatever path is smoothest according to the gradient, and stochastic gradient descent is going to follow some jiggy-jaggy, ziggy-zaggy, wonky way of getting there. And it's going to eventually go like that, right? Okay. Wouldn't it be nice if we could smooth out stochastic gradient descent to make it more like batch gradient descent, but not so darn computationally expensive and slow? Enter momentum. What if at first we went in some stochastic direction, and next time we went in another stochastic direction? You see that on average that's going like this, right? And if the third time we went like that, and the fourth time we went like this, and the fifth time we went like that, and the sixth time we went like that, it has to, in the end, get there, because we know that the sum of all these patterns is the same thing that a true gradient descent step would do. Therefore, if we have a degree of momentum, meaning we retain some of the previous gradient and add it to the coming gradient, that'll kind of smooth it out, right? Okay, so the whole idea of momentum is this. Let's see. So first let's do SGD. Stochastic gradient descent does forward prop. Wait, we call it activate in your implementation. By which I mean activate, followed by compute error on the output layer, and then back prop, which computes the error for all the preceding layers, followed by update gradient, which computes the gradient for all of the layers, followed by update weights, which is basically weight plus equals learning rate times gradient, right? So these are all the steps in stochastic gradient descent. Okay, and that is for I from 1 to n. Okay, the big difference with momentum is, can't even show you because we didn't, right here, we set gradient to 0. And right here, we don't set gradient to 0. Here we scale down the gradient. In fact, let's put it this way. I'm going to get rid of this one, and I'm going to say double momentum equals 0. Then I'm going to say gradient times equals momentum. This is stochastic gradient descent as you know it. Do you understand that? Okay, because this line right here will set your gradient to all zeros, and then when you call update the gradient, that's going to add to your gradient all the values that you computed from the most recent pattern. Well, now if we increase your momentum to say 0.1, do you see what effect that will have on your code? Now your actual gradient, by the time it reaches this update gradient line, will be 0.1 times what it was before plus the new gradient for the new pattern. And if we do a lot of momentum, like 0.9, that would be a lot of momentum. Now it's going to retain 90% of what it was before plus the current pattern. And so that's going to really smooth it out. But it's also going to kind of make it take bigger steps, right? Well, you'd think, until you cross over the optimum, and then all of a sudden your gradient vectors start fighting each other, right? Which slows you down. And if you think about it, isn't that kind of what you wanted? So it's not physics momentum, because physics momentum would mean once you cross the finish line, keep going, right? Well, don't think of physics because it's not physics. And in my opinion, they shouldn't have called it momentum. They should have called it something else. But what it does is it's more like a memory. It remembers part of the gradient from before and keeps on adding it to you. This tends to have positive effects in learning, but sometimes it screws up learning. So should you use momentum? I don't know. Here's a general rule. I almost always learn without momentum. Why? Because I know it will work. It just might take longer to train. And then after it's done, then I say, well, it's already done, so who cares? And then I walk away. There are a lot of cases where people have found that it's better to use momentum. It learns much faster. Sometimes it even learns better. So it's a good thing to know about. It's just not reliable enough that I really like it. But there's a lot of really nice theory behind it, and it seems to be better more than half of the time, so momentum is probably a good thing. It also makes stochastic gradient descent more like batch gradient descent without paying the expensive cost of having to do batch gradients.